So to solve this type of problem, you need to know the formula C equals lambda nu, where lambda represents wavelength and nu represents frequency. And you need to know that the speed of light, or C, is 2.998 times 10 to the 8 meters per second. So you just plug and chug from here. 2.998 times 10 to the 8 meters per second is equal to the wavelength, which we're trying to solve for, times the frequency, which is 4.0 times 10 to the 15th hertz. Or hertz are equivalent to seconds to the negative first power. So we'll just replace that so that our units cancel out nicely. Then we can set this equation equal to wavelength. So it would be 2.998 times 10 to the 8th meters per second divided by 4.0 times 10 to the 15th seconds to the negative first power. And you see that seconds cancel, and you will get your wavelength in meters, which is the correct unit for wavelength. And you, dividing this out, you'll get 75 nanometers. So you need to know that the de Broglie wavelength is equal to Planck's constant, which is 6.62607 times 10 to the negative 34 joules per second, over momentum, which is equal to mass times velocity. And in this problem, you're given the velocity and the mass of the electron. You also need to know, though, that he gives you the mass in grams, but for these problems, mass needs to be in kilograms, so we can convert that to kilograms so that all of our units will cancel out properly. So 9.11 times 10 to the negative 28 grams divided by 1,000 grams gives you 1 kilogram. You get 9.11 times 10 to the negative 31 kilograms. So now we can plug all this information in, plug in Planck's constant, which is 6.2607 times 10 to the negative 34, and then we divide by the mass, which is 9.11 times 10 to the negative 31 kilograms, and we multiply that by the velocity, which was given to us, which is 5.97 times 10 to the 6th meters per second. And when we solve this problem, we get that the wavelength is 1.22 times 10 to the 9 meters, or 0.122 nanometers. And that is the final answer. To be able to do this problem, you need to know that energy is equal to h nu, h being Planck's constant, which is equal to 6.626 times 10 to the negative 34, and nu being the frequency. However, this question gives you wavelength, so you need to put this equation in terms of wavelength. And you can do that by substituting c over lambda for nu, because nu is equal to c over lambda. So where lambda is wavelength and c is the speed of light, which is 2.998 times 10 to the 8th meters per second. So now that we have this equation, we can plug in the information that was given to us in the problem. And you need to realize that he gave you wavelength in centimeters, so we need to convert that into meters. Do that by multiplying by 10 to the negative 2 meters, and we get 0.150 meters. So energy is equal to Planck's constant, or 6.626 times 10 to the negative 34, times the speed of light, which is 2.998 times 10 to the 8th, over the lambda that we just found. So we'll plug that in right here. and then this will give you energy in joules. So when we work that out, we get that energy is equal to 1.32 times 10 to the negative 27 joules. But he wants the answer expressed in terms of kilojoules per mole, so we need to do some conversions. So 1.32 times 10 to the negative 27 joules. We'll divide that by 1,000 to get it into kilojoules. And it wants kilojoules per mole, so we will multiply by Avogadro's number to get it in the correct form. And when we do that, we get 7.97 times 10 to the negative 4 kilojoules per mole. And that is the final answer.